Okay. So let's talk about low latency memory. I think this is really important going forward. We need to design fundamentally low latency architectures because we need to solve the hardest problems. And I think latency is something that we really need to solve. So I'm going to deconstruct this again. Maybe we don't care about energy. If we have enough speed, we can solve everything, right? I don't know. Of course, this is a joke, but I think we need to think about that. And you've already seen this. Clearly, main memory latency lags behind. Some of this is fundamental. Some of this is not fundamental. But the question is, how do we actually get this curve up like this as opposed to like this? And actually, if you look at a closer look, some of the latencies are increasing. Actually, we recently published this paper in Sigmetrics that I mentioned earlier. Some of the recent memory technologies, like DDR4, increases the memory latency to get higher memory bandwidth. And as a result, you lose performance in some applications that really care about it. Actually, many applications in our studies, if you move from DDR3 to DDR4. Doesn't sound like a good idea, right? Actually, technologies that improve memory latency improve performance. In GDDR5, for example, reduces memory latency compared to DDR3. As a result, you improve performance in many applications. It also improves memory bandwidth, so that's good. But of course, DDR5 comes with a huge power cost. So that's the paper analyzes. But I think we need to rethink the memory latency because it's critical for performance in many applications, clearly. So it's a significant limiter of system performance and energy efficiency, and it's becoming increasingly so with higher memory contention. It exacerbates the bandwidth need, it exacerbates the quality of service problem. And it increases the processor design complexity because of a lot of mechanisms that we've discussed. This is actually a slide that I used as early as my PhD proposal. That's why it has the UTEC sign over here. I worked on tolerating memory latencies. Maybe I'll talk about that. I don't remember if I include that in the slides or not. I worked on something called run-ahead execution, which is really a simple form of tolerating memory latencies. But if you look at the process techniques we use to handle latency in systems today, they're all processor-centric. This is because of the processor-centric mindset that we have. Caching, prefetching, multi-threading, auto-order execution, they're all heavily employed. They're all developed in the 1960s. We've been optimizing them for 50 years or more. They sometimes work, sometimes don't work. And there are benefits and upsides and downsides to all of them, clearly. But none of them fundamentally reduce memory latency. They're all there to tolerate memory latency or reduce it from the processor's perspective. The latency is there. You're really bringing the cache line earlier by prefetching, such that the processor doesn't see that latency. But the latency is there, and it's increasing, actually. So, I have run-ahead execution. So maybe I'll briefly talk about run-ahead execution. This is deja vu, but and I shouldn't say I'm guilty of it, but I had the processor-centric mentality also in the past. Basically, you want perfect caches ideally, right? But that you don't get that, unfortunately. So auto-order execution, what it does is it tolerates some of that latency, but most of the time it stalls because it doesn't have a large enough instruction window to process ahead. And it computes after the stall is done because this latency is too long to tolerate. And then later another cache miss comes, your instruction window becomes full after some point and you stall again. So it doesn't sound good, but this is the reality. This is why you see Google showing results. Most of the time you're in the red, right? You're in the green only 10 to 20% of the time. Most of the time you're waiting for data. So in my PhD thesis, I worked on an idea called run-ahead execution. The idea is very simple. It's a processor-centric idea. Whenever you get to a long latency cache miss, whenever your instruction window becomes full, you checkpoint the architectural state. You enter this speculative processing mode where you keep executing the program. Some of the values are not available. You basically ignore them. Don't do anything with them, but the values that are available, you can do prefetching, right? You can warm up your caches. And the hope is that while in this run-ahead mode, speculative execution mode, you get to the second load miss if it's independent of the first load miss. Now I can start that early. You exit run-ahead mode when the first miss that caused you to enter run-ahead mode comes back, and you flush the pipeline, you pay some penalty, you re-execute the load, now you get a hit because you just serviced it, it's in the cache. Now you keep computing, at some point the second miss completes, and whenever the processor reaches the second load, it now hits in the cache. Now you've saved a lot of cycles because as opposed to stalling, you've done some pre-processing very accurate pre-processing of the instruction stream and did a lot of good prefetching as opposed to stalling. And I like this idea, of course. No biases here. And Sun liked this idea also. This is data that Sun presented, one of their chief architects. They implemented this in Sun ROC processor. They called the Scout threads. And they showed that this is on some OLTP, online transaction processing workloads that they were caring about at that time. Clearly Sun is out of business right now. Hopefully it's not because of run-rate execution. Hopefully it's because of something else. But basically they showed that if you have a small cache, you get 40% better performance with run-rate execution. And alternatively, you can use run-rate execution with a small cache and get the performance benefits of a large cache without run-rate execution, clearly. So there are good benefits to this idea, clearly. And this is our original paper, and this is a shorter version of it. And clearly there are a lot of issues with the idea that we developed in my PhD thesis to solve the problem that I'm not going to talk about, how to make it efficient, how can you parallelize dependent cache misses. That's also important, I think. It's not easy, it's a hard problem, but sometimes you can do that. How do you do that? How do you figure out when you're in the weeds of wrong path, and how can you figure out that early? But again, this is an example of this processor-centric mechanism that's out there that adds more complexity into the system. Maybe not as bad as adding huge buffers. It's actually very low cost compared to having a huge out-of-order execution engine, but it adds more complexity into the system. Why? Because we're not reducing the latency fundamentally. If we actually had mechanisms to reduce latency fundamentally, maybe we have a much better system design. So let me talk quickly about the latency inefficiencies that we've been targeting recently. So now that I maybe think better, it's a good idea to solve the problem at the source of the problem. So modern DRAM is not designed for low latency. Main focus is cost per bit. And modern DRAM latency is determined by the worst case as opposed conditions and worst case devices. Much of memory latency is really unnecessary, actually, even with the current DRAM designs. And I'm going to talk about this because we probably won't have time for this, but I'll have a lot of slides for that. So basically, we've been focusing on reducing the memory latency at the source of the problem as opposed to in the destination of the problem, which is the processor. So, okay, we're going to talk about two different sources of latency inefficiency. I think I'm not going to talk about this one. Okay, I don't know why it's repeated. Basically, the design of DRAM microarchitecture is not for low latency. We could actually design DRAM microarchitectures that can reduce latency significantly at some overhead. And we have some works. Those are in the slides. But I'm going to talk about this part a little bit. Basically, today we have a one-size-fits-all approach to latency. We have the same latency parameters for all temperatures. Although we know that at low temperatures, you can reduce the latency significantly because you have a lot of charge. And charge sharing becomes much faster. The same latency parameters for all DRAM chips, for all parts of a DRAM chip, for all supply voltage levels, and for all application data. So if we actually think about latency differently, such that it's very heterogeneous, and we adapt it to different conditions, different data, we can actually get rid of a lot of the latency. I call this a fixed latency mindset. Reliable operation latency is actually very heterogeneous, and we've been trying to find out, hopefully dynamically, and use the lowest latency one can reliably access a memory location with. And I'm going to give you some ideas over here. Since we don't have a lot of time, I'm not going to be able to talk about a lot of the ideas. Adaptive latency DRAM is the simplest idea. As we go down, it becomes progressively more complicated, but you get even more benefit if you keep going down. Well, some of them are different also. So we recently, because of the work that we've done in this area, we recently figured out how you can generate true random numbers in DRAM. As you reduce the latency, some cells start failing randomly with 50% probability. And you can figure out which cells those are, and then you can generate a random number by actually getting the data out of those cells by reducing the latency. And this gives you a very high throughput, low latency random number, true random number generator, because these are actually true random numbers because they're based on process variation. Okay, there's a bunch of other things to be done. Basically, we would like to find the source of latency heterogeneity and exploit them to minimize latency or create other benefits like what we've talked about. Let me give you the simplest ideas, and then we can decide whether to continue or whether to switch to the other part of the lecture. So we have heterogeneous manufacturing and operating conditions that leads to latency variation and timing parameters. I like visualizing it like this. You have different DRAM chips, and they're basically on different sides of the reliable operation latency is different for all of them because of manufacturing variation. And reliable operation latency of different cells inside the DRAM chip is also different. So there are some slow cells in a DRAM chip, there are some fast cells. So today we use DRAM latency as delay specified in DRAM standards. Somebody says this is the latency that you should wait, and we obey it. But that doesn't reflect the true DRAM device latency, because we have imperfect manufacturing process and latency variation. The way DRAM latency is determined in those standards is based on how much profit you can make as a DRAM manufacturer, which means how much you can maximize the yield. Basically, you have all of these DRAM chips. Based on some manufacturing variation, they end up in different parts of this DRAM latency spectrum, and you add some margin to it, and you specify that latency over here as standard latency so that you can maximize your yield in the DRAM chip. So most of these DRAM chips are acceptable. There is a very small tail end of the distribution that's not acceptable, and you discard them. So if you pick your standard latency high enough, you can maximize your yield clearly. But this doesn't mean that you cannot operate this DRAM chip at much lower latency, right? So as a result, we have these conservative timing margins. You can think of this as a timing margin, right? You chose your standard latency for whatever reason. Some of it is timing margin, some of it is yield considerations, but it's very high compared to what you can operate this particular DRAM chip with and DRAM cells with. So you have a conservative timing margin, and DRAM timing parameters are set to cover the worst case. And there are two different kinds of worst case. One is operating conditions like temperatures. Basically, we specify the latencies such that DRAM chips are still operate correctly at 85 degrees Celsius. Actually, it's 95 degrees Celsius in some standards. But common case is not 85 degrees Celsius. Actually, it takes a lot of effort to increase the temperature of a DRAM chip to 85 degrees Celsius, especially if you're in a server. If you're 3D stacked, you can more easily do it. But if you're not 3D stacked, it's very hard, actually. So we're wasting a lot of latency. So this enables a wide range of operating conditions. So worst case devices, as I showed you earlier, basically we're really tolerating DRAM cell with the smallest charge across any acceptable device. That's the process variation. We want to tolerate process variation at acceptable yield. And this leads to large timing margins for the common case. So we wanted to understand and exploit variation in DRAM latency, and we used our infrastructure that we built for retention time purposes to understand the latency variation, and I've already given you examples of this. And one of the ideas that we've developed is this, basically. We wanted to change the DRAM timing parameters online and adapt it to the temperature and the DRAM chip. There are two components of this. The way we envision this is that DRAM manufacturer provides multiple sets of reliable DRAM timing parameters for each DIMM for two different temperatures, 55 degrees Celsius, 85 degrees Celsius. And the system monitors the DRAM temperature and uses appropriate DRAM timing parameters for that particular DIMM. Of course, this increases the testing cost a little bit, but it's not that bad, probably. And if you use two temperatures, it's not that bad, I think. And we actually analyzed what are the reliable operating temperatures averaged across 115 DIMMs that we tested with our infrastructure. At 55 degrees Celsius, on average, you can reduce the read latency by about 30% and write latency by about 55%. Of course, there's a distribution across different chips, and some chips you can actually reduce the write latency by about 80% or so, it turns out. If you actually are able to specify this, now you can actually reduce the latency significantly. So I think we're really trying to tolerate the latency, and much of the latency that we're trying to tolerate with these complex mechanisms are actually unnecessary. If we can enable something like this, you can get rid of a lot of the latency. And the latency reduction for each timing parameter is in the paper. Actually, we released all of the results. You can look at every single chip that we've analyzed in this HPCA 2015 paper. And we actually did some of the real system evaluations. Of course, not the dynamic mechanism, because there's no dynamic, at least publicly available dynamic memory controller that allows you to change the latencies currently. And this AMD system enables us to change the BIOS, to change the latencies. That's true. Actually, gamers use this sort of frequency increase as well as latency reduction a lot. Except in this case, we were able to rigorously test our chips to figure out the reliable operation latencies that we could use. And we used those latencies in the system. And we did some performance evaluations, and we essentially see significant performance improvements if we use the latencies that we determine by testing at 55 degrees Celsius. Okay, so basically you improve performance by 14% in real workloads over here. Yes?
I have a very simple question. Maybe it's common knowledge, but I don't know.
Sure.
So how did you just increase the operating frequency, or is there something that you can manipulate in the driver?
Well, you mean in this particular real system?
In this measurement.
So in the measurements we've done, let me go back. There are two types of system. Basically, you change the timing parameters in the memory controller. Memory controller basically normally uses some timing parameters that are specified in the DRAM standards. Activation latency, let's say 13 nanoseconds.
So these are hard-coded values.
Exactly, these are hard-coded values in the memory controller. We reduce them basically.
Okay, and then you measured for e.g. for writing, you wrote a number.
Exactly.
And then you go down to the smallest number, and afterwards you instantaneously read the number again.
Exactly. If it's correct, then basically you can reduce latency. Of course, you need to do rigorous testing. Some of these workloads we tested for actually 3 months. Ran them for 3 months, and we didn't get any errors with the latency parameters that we deemed was good for those particular DIMMs. And these are detailed in the paper, of course. If you're interested in the really detailed studies, we release a source code of how to do this also. Okay, but in these real systems, actually, you can configure it in the BIOS. So in the real system, this AMD has, for example, in the BIOS, you can set the timing parameters in a limited form. It's not as configurable as our memory controller, of course, which is FPGA based. You can do it in a real system also. How many of you are hardcore gamers here? Okay, no one. Okay, one. Have you reduced the latencies in yours?
I tried, but I have a bad set of RAM, so I couldn't.
I see, okay. But you tried, essentially. So basically what we're proposing is a more rigorous method of identifying these latencies through testing and really specifying them, as opposed to trying it out and seeing if it works, right? And most of the cases it works, actually. But with bad RAMs it may not work. Okay, so basically you get real performance improvements over here. And I don't think our measurements do real justice, but these are real performance improvements that you achieve on real systems. Okay, this is some preliminary evaluation. Reducing latency is also good for reducing energy because you're activating things for much less. And we see that you reduce power consumption, but we didn't have very good power models back then. But I believe the power per consumption benefits are actually higher. So this is actually the simplest mechanism that I'm going to describe. This is a simple mechanism to reduce latency. It gives you significant system performance and energy benefits, and benefits are actually higher at low temperature. So it's low cost and low complexity. Of course, there's a disadvantage. Somebody needs to test these DIMMs. So I think it's not that bad, actually. And it's not that difficult for low temperatures. And in all of our latency reductions, we actually assume some additional margin. So the similar margin that's employed in existing systems, we actually have that also. So we don't get rid of all of the slack. So later we decided to build actually online profiling mechanisms. While the system is running, can you determine the latency, lowest latency you can operate DRAM with? If you have ECC, for example, in the system, you can reduce latency, see what kind of errors you're getting, you can adapt to it. So there are different types of latency variation. ALDRAM exploits this latency variation across time and across chips. The next question we asked was, is there also latency variation within a chip? If you look at a DRAM chip, is there a latency variation? And the answer is yes, actually. And this is some example data that we have. Basically, if you reduce the activation latency to 7.5 nanoseconds from, I believe, 13 nanoseconds over here, most of the time you don't get errors. This is a density plot. Basically, this is the probability of error increases with the darkness of the color that you see over here. So most of the time you have white, basically meaning that you have no errors. This is cache lines, this is rows. Basically, this is a two-dimensional structure of the DRAM array. And you can see that only these parts of the DRAM chip are vulnerable. And you can see that the errors are really constrained to some particular cache lines, meaning that there's a lot of spatial locality of these errors. So you can actually design things to correct these also, and that's exactly what we did. Or you could actually expose these different types parts of a DRAM chip to the memory controller, and memory controller uses different latencies for different parts of a DRAM chip. Okay. So basically, DRAM timing errors are concentrated on certain regions. The idea is to have a software transparent design that reduces latency. We divide memory into regions of different latencies, and we expose this to the memory controller. Memory controller uses lower latency for regions with slow cells and higher latency for other regions. Of course, you specify the latencies also. Again, this is an intelligent memory controller. Memory controller also can figure this out on its own. That's the next work. So we actually looked at 3 different DIMMs. These are real profiles of real different DIMMs. You can see that if you specify two different latencies, 10 nanoseconds, 7.5 nanoseconds, most of the cells over here require 10 nanoseconds in this DIMM, require 10 nanoseconds TRCD activation latency to operate correctly. A small fraction can be operated even faster, but if you look at this DIMM, more than 99% of the cells can be operated extremely fast, 7.5 nanoseconds. Well, there are these numbers. So for example, this DIMM happens to be not a bad DIMM, it's a good DIMM. You can reduce the latencies a lot in this one. This DIMM, not so good, but it's still good. And then if you expose this two different latencies to the memory controller, now memory controller can access 99% of the cells or rows at 7.5 nanoseconds and remaining 1% at 10 or 13 nanoseconds. And the upper bounds, of course, 100% of the cells are actually accessible at 7.5 nanoseconds. That's called low latency DRAM. And these are the results that we get. Average across 40 workloads, and maybe these are not the most memory intensive workloads, we get significant performance improvements. So of course your performance now depends on the distribution of the cells in a DIMM, but that was true for adaptive latency DRAM also. It depends on the DIMM in that case. So you get more than 13% here, almost close to the ideal here, because more than 99% of your cells can be accessed fast. So clearly this is more sophisticated right now. It reduces latency even more significantly than adaptive latency DRAM because you can exploit within chip latency variation. But now you need to determine the reliable operation latency for different parts of a chip. Now you have even higher testing cost. And you have a slightly more complicated memory controller. Your memory controller needs to really record the information for different parts of a DRAM chip. And this is the paper that talks about a lot of this. And again, we open source our source code so you can actually replicate the results. So there are a lot of other questions that we can ask. The question is, do we want to continue more? Yes, please.
Just when the memory is aging, I guess the latency is increasing as well?
Could you say it again? When the memory is
aging?
Aging, yes, that's a great question. So yes, we actually looked at a lot of these issues in terms of aging. That's exactly why we wanted to develop online profiling mechanisms. Over time, you keep testing the memory while the system is running, and you adapt the latencies to these aging issues. So what we've assumed in the previous works is you add some margin to tolerate aging issues. If you age, you eat away from that margin. So we're not cutting all the slack, all the timing slack. But I think you can cut even more slack from the timing if you actually have online profiling mechanism. And that's the next work. So for short-term aging, it's not a problem. We've actually done tests for like months. It's fine, the latencies if you cut the slack. But we don't know the exact results for 5 years from now, for example. That's why we want to do the online profiling mechanism. So the question is, do we want to talk about online profiling a little bit? Or do we want to go to the next part and then conclude? Any thoughts? Online profiling, somebody says. Anybody wants to counter that? Okay, I'll keep going for some time. I mean, this is only one of the works. I'm going to give you the basic ideas. This is actually really interesting, I think. Basically, we wanted to understand why these variations exist. I'm not going to talk about online profiling only because I think ECC is very important, and ECC is going to be there in chips, so we want to use both of them at the same time. So if you look at a chip over here, there's latency variation across the row. Things that are close to the sense amplifiers are fast. Rows that are close to the sense amplifier are fast. Rows that are far away from the sense amplifiers are slow, just because of the interconnect delay that you have. That's true for the word line driver distance also. Across the columns that are closer to the word line driver are fast. Columns that are farther away from the word line driver are slow. So there's an inherently slow part of the chip, and there's an inherently fast part of the chip. Of course, it's a super simplification. There are more things at play, and those are discussed in the paper. Now, all else being equal, clearly there's a organization-dependent variation in the latency. And we call this designing this variation aware. And we wanted to actually use this for profiling at very low cost and at very high speed, and finding out the lowest latency. So if someone provides you the inherently slow region, they tell you this is the part that you should test once in a while to figure out what's the lowest latency you can access DRAM with, then this works. Basically, you test only those parts, and you say this is the lowest latency I can access these parts with, And I'm sure that it's going to work for other parts, assuming that's the only type of variation you have in the system, of course, right? And that's the idea we have over here. There's inherently slow parts. We profile only those to determine the minimum latency. And you determine all types of latencies for those. And this enables dynamic and low-cost latency optimization. Of course, this requires someone to specify what those parts are. You can discover these parts also, actually, by reverse engineering with the infrastructure that we have. But I think it's better to rethink the interface between the memory controller and DRAM, just like I've been proposing for Rowhammer earlier. But of course, this is not the entire story, right? There are parts that are slow because of random process variation. And I believe those parts are more easily corrected with error correcting code. So these design variation, they're localized errors, but these random errors, they're much harder to predict. They're not based on any systematic variation, they're based on random variation. So error correcting codes are a very good fit for protecting these cells and also figuring out whether you can reduce latency significantly. And online profiling is a very good way of determining the lowest latency you can operate things with. So I'm not going to give you the exact mechanism, but it combines error correcting codes and online profiling. It figures out what is the lowest latency you can operate this region with. It changes the latency and sees if you get random errors. If you don't get these random errors, that's great. If you get these random errors, you can hopefully cache them with error correcting codes, and then you can back off. You can increase the latencies. And that's the idea over here. And you can do this once in a while over time because the profiling overhead is very low. You know these regions. If you had to profile the entire DRAM chip, that could take some time. But if you know these regions, you could actually do this relatively fast. And this way you can reliably reduce DRAM latency, even at high temperature conditions. And we tested a bunch of, again, a large number of DRAM chips, and we found out that this is adaptive latency DRAM, the idea that I described earlier. It reduces latencies pretty well on these DRAM chips. But if you do this sort of profiling, you can reduce latency even more because you're taking advantage of ECC as well. And actually, if you change the error correcting codes a little bit, such that you correct the errors better, without increasing the capability of the error correcting codes, but just shuffling the data better, you reduce the latencies even more. And that's true for write latencies also. And now you actually reduce latency significantly at high temperatures as well. And this leads to significant performance improvements that I'm not going to talk about. So the big advantage of this is now you can automatically find out the lowest reliable operating latency at system runtime. So the production time testing cost is low, and you can handle a lot of these aging related issues that you mentioned, for example. And in the paper we talk about those aging related issues as a motivation for this sort of profiling. And it reduces latency more than with prior methods because you take advantage of the ECC in a good way. And I already said that. But of course, the disadvantage is this requires knowledge of inherently slow regions. And as I said, having a better interface that exposes these regions is a good idea. It requires error correcting codes, but I think going forward, these error correcting codes will be there in all of the DRAM chips. Yeah, clearly runtime profiling overheads needs to be in check, kept in check. And this is a paper that has a lot of data and a lot more detail on the mechanism that I won't go into detail about right now. Okay, this switches the gear a little bit, so maybe I'll skip this one. I'll leave the slides. But we've been actually looking at voltage, latency, reliability relationship and how to trade off between those. There's a lot of voltage margin in DRAM chips also, and this is what we've discussed in this work. And let me skip a lot of this. But basically, this is the work that to analyze the voltage. And in this case, for example, if you reduce the voltage, you start getting errors. But there's an interesting trade-off. You can actually increase the latency, because at reduced voltage, you're operating more slowly. If you increase the latencies, you can get rid of those errors. So there's an interesting sweet spot in terms of energy performance trade-off. You can reduce the voltage very aggressively, and you can correct the errors by increasing the latencies. And it turns out by doing this intelligently, you can get a lot of performance, a lot of energy improvement in existing systems. But I don't think I have time to talk about that, so I'm going to skip that one. I already talked about this random number generation, which is really fascinating to me. But again, I'm not going to talk about that. So there are a bunch of other ideas that are inside these slides, which we don't really have time to talk about, since we have only 4 hours, right? maybe I'll talk about one of this. This is very recent work. Let me see how many other slides that I have. Sorry. Do we want to talk more, or do we want to switch to part 5? Any thoughts? I think people are getting a bit tired. Okay, let me talk about some of the most recent works. This is actually presented at ISCA a couple of weeks ago. And I think this is, we've been looking at changing the DRAM substrate to reduce latency also. And we call this the copy row substrate. And we wanted to target multiple things actually over here: access latency, refresh overhead, and row hammer type of vulnerabilities. If you look at conventional DRAM, this is the DRAM subarray. And you activate, and the data goes into the sense amplifiers. Now, we change the conventional DRAM such that you have two different types of rows: regular rows and copy rows. It turns out these copy rows enable something that can help multiple things. You have two different decoders. Copy rows are very small number, 1, 8 maybe. And the idea is you can enable a row copy operation. Basically, you activate this row, which brings data into sense amplifiers, and then you activate this row, you copy the data over here. So we knew about this actually before with row clone. So it's very similar to row clone, but now you have two different copies of the same data. If you had the primitive to do multiple row activation, if you activate both of them at the same time, because you have two different copies of the same data, chart sharing is much faster. Now you can access that data much faster. That's the idea. This is one way of reducing latency in DRAM if you have this sort of substrate. And there are multiple use cases. As I said, I just described the idea of crow cache, which reduces the access latency. You activate two rows at the same time, and they contain the same data because you've activated and placed into the copy row. Okay. You can actually reduce the DRAM refresh overhead. Some weak rows, so for example, with weak cells, you can remap them to strong copy rows. And that way you can actually get rid of the weak rows, and we have a lot of analysis. And we also show that you can protect against row hammer if you have these copy rows by copying the vulnerable or hammered rows into this copy row substrate. And it turns out this leads to significant performance and energy improvements, and it has very little hardware overheads. And this is an example of changing the DRAM microarchitecture to enable low latency, but also other benefits. And I think this sort of ideas need to be explored even more going forward, because the existing DRAM substrate is really not that optimized for latency for sure. Okay. So I think, let me see. I think I'm going to conclude the latency part, but I'll talk about just this part. This is the paper that I mentioned that was published in Sigmetrics. We did this relatively comprehensive. I don't want to call it very comprehensive because there are always more workloads that you have, right? We looked at many workloads and many, I think 9 different DRAM types and more than 100 workloads. And we wanted to understand which workloads are better fit for what type of DRAM. And I think there are a lot of insights over here, but one of the big insights, in my opinion, is newer memories sometimes make the trade-off, actually usually make the trade-off of increasing the latency for increased bandwidth or for some other reason. And that's not a good trade-off because a lot of the workloads are still latency bound. And I think other people have found this, but this is perhaps a rigorous study that shows this. And I'd be happy to talk about that. I think there's a lot more work to be done like this. One of the interesting comments that we got when we submitted this paper is, why don't you do this on a real system? And it's very interesting to have this comment because unfortunately there's no real system where you can plug in 9 different types of DRAM and have a single infrastructure where you can do fair comparison across many workloads. So it's interesting not to have this comment, I think. I wish I had that system. But that system is a really behemoth to build, right? I don't want to build that system because designing even a single memory controller, a DDR3 memory controller, is such a pain. It's one of the most complicated things, actually. Okay, so let me try to conclude. Any questions so far? Okay, yes, please.
Just because the DDR controller is so complicated,
yeah.
so the sort of exposing more information and making it more flexible,
Yeah.
how viable is it?
Makes it even more complicated, right? Yeah, I think so. But I think we're already paying the penalty of complicated controllers. At least we can do more with them, right? Right now we're designing these huge complicated controllers and they're dumb. Why don't we add a little bit more complexity and make them more intelligent and have a much more balanced system? That's basically the argument I have. But I also think that maybe we can also simplify the protocols. So we didn't talk about that as much. But the protocols that we have in memory today are not that great. And there are so many timing parameters, so many different things that a designer needs to think about. Maybe we may want to think about more asynchronous designs again. Right now it's synchronous DRAM, that's why we have so much so many timing parameters. I think going back to more asynchronous designs can help. And also I think, I didn't talk about that, but I'm a big believer in using more automated techniques inside the memory controller. We did this work in 2008, which was published in ISCA 2008, where we used reinforcement learning. And we essentially designed a memory scheduler that used reinforcement learning as opposed to a human designed policy. And we showed that that memory controller is much higher performance than a human designed memory controller. Because humans, I think, cannot think about so many different timing parameters and dimensions and complications in memory. So if we can automate this procedure such that controllers use machine learning techniques, I think that can also solve some of these issues. But of course we need to build insight as well. I'm not a full believer in the machine learning part, but I think we can make use of it. Yes?
So after all the latency optimizations, where are we in that latency bandwidth curve in the beginning?
Oh, okay. I don't know, because I didn't plot that. That was for DDR, right? So basically where we are, I think we can get latency improvements much higher, basically. I think we can. We never aggregated the results because it's still ongoing research, and we never combined all of the ideas because a lot of these ideas are orthogonal in the end. The structural ideas are orthogonal to the timing margin reduction ideas, for example. So I believe you could get to 5x improvement in latency, frankly, if you aggregate them. But that's a good question. We should do that study at some point. But there are always newer ideas to explore.